My name is Tracy Hunt, and I'm going to be presenting the research findings from two articles that detail how the study of caves and speleothems can be used as paleo proxy records to study the climate of the past and predict the climate of the future. Speleothems include cave features known as stalagmites, stalactites, columns, and flowstones. These features are found in caves all over the world. All of these features form slowly over time from the mineral deposit in groundwater in the caves. As the water moves through the caves, the minerals in the water are left behind and build up to form these features. When they are studied, the tips are generally the youngest part of the record, with the base or the core being the oldest. By examining the isotopes evident in the bands of minerals in the speleothems, researchers can draw conclusions about past climate data. In the studies we are looking at today, speleothems are used to gather data about precipitation or lack thereof in the past. The first region we will be looking at is located in the Qinling Mountains in central China, the Diyu Cave. The Diyu Cave is located on the southwestern slope of the mountain range. The cave is about 2 kilometers long, or about 1.24 miles, with very high relative humidity at around 97%, and it has a high concentration of CO2. This area is very heavily impacted by monsoon season, with an average annual rainfall of about 1,100 millimeters, or about 43 inches. The average temperature of the cave is around 13 degrees Celsius, or 55.4 degrees Fahrenheit. While my presentation today is focused on speleothems as paleoproxy records, I want to take a moment to discuss how caves are also common sites for historical records. The Diyu Cave features inscriptions dated from the years 1520 to 1920 CE and demonstrates that local ancient people visited the cave frequently during this time. These inscriptions depict 7 drought events that took place during these years, and these historical records are directly reflected in the isotopic evidence present in the cave. To study the isotopic evidence, scientists selected stalagmite DY1, which is dated from 1265 to 1928 CE. When scientists examine the oxygen-18 isotopes in the stalagmite, they are able to extrapolate data about precipitation events. Droughts are reflected in the isotopic data with elevated strontium to calcium ratios. The drier conditions cause longer water resistance times and decreased drip rates. In Figure 5, the black triangles at the top reflect the number of trips made by the local people to the cave, and the gray bars are drought events. There is a direct correlation between the drops in oxygen-18 isotopes and the trips made to the cave. The scientists use the data for the regions in the Qinling Mountains to build a model that predicts isotopic 18 levels through the year 2042, as seen in the yellow region of the graph above, Figure 6. The low points circled on the graph are drought events, and the model predicts much lower O18 levels and a higher likelihood for drought events in the future. It is predicted that precipitation levels will fall below the average of the last 500 years in China. One of the drought events in the model was predicted to occur in the 1990s, and this event did occur. This region of China is a recharge area for an important water reservoir, as well as home to the endangered giant panda species. Drought events in this area will continue to have a large negative impact on the people in the biological sphere for this area. The next region we will be covering are 2 caves in southwest Morocco, the Ifolki and Win Timdouin caves. These caves are located around 2.5 miles apart from each other in the western High Atlas Mountains on the southwestern coast of Morocco. Both of the caves were formed in the Jurassic Age and are formations of limestone. This region experiences most of its rainfall between December and February and can be characterized as a wet season in the winter and dry in the summers. The annual average temperature of the region is 14 to 19 degrees Celsius, or 56 to 66 degrees Fahrenheit, in the winter, and around 33 degrees Celsius, or 91 degrees Fahrenheit, in the summer. Various ocean currents are depicted on the image shown because the rainfall in this region is correlated to sea surface temperatures. The stalagmites studied in the Ifolki and Win Timdouin caves in Morocco are called IFK2, which is dated to have formed between 459 and 2010 CE, and stalagmites Win 2 and Win 3 represent an age range of around 2010 and 1800 years old. As shown in the studies conducted in the Diyu Cave, the inverse correlation between the amount of precipitation and the isotopic O18 levels in the Ifolki and Win Timdouin caves is consistent. In these caves, the isotopic O18 levels can be used to reconstruct the shifts in precipitation in the area. The area has experienced very severe multi-year droughts in the 19th and 20th centuries, and these events are recorded in the isotopic evidence found in the stalagmites studied. When the scientists built models to reconstruct the data, there is a trend upwards that is very similar to the hockey stick effect that we are seeing in temperature climate data all over the world. We are experiencing a sharp uptick in higher temperatures and drought events, and the isotopic evidence in the caves is reflecting this trend as well. This region's precipitation events are directly affected by sea surface temperatures and increasing greenhouse gas emissions. As these temperatures rise and we experience changes to the North Atlantic Oscillation and Atlantic sea surface temperatures, we can understand the effects of decreases in precipitation in the area. By studying the Speleothem records in the caves in Africa, scientists were able to gather Paleo Proxy records that reflect the climate variability of the past in the region that has significantly less recorded climate data compared to the Northern Hemisphere. In conclusion, we can see how important it is for scientists to continue to gather Speleothem paleoproxy data around the world to be able to better understand the past and build climate models to help us better prepare for the future.